Okay, so last time we had been talking about the harmonic oscillator in one dimension. So let's just review the things that we'd found. Okay, so first of all, the Hamiltonian is p squared over 2m plus a potential, which is quadratic in the position. And we were looking for, our goal was to solve the time-independent Schrodinger equation for energy eigenstates or stationary states, which in the position representation, which is our first thing, has the form minus h bar squared over 2m, two x derivatives, plus the potential, acting on the wave function, not the ket. Okay, and that's because the derivative operators act on wave functions, not on kets. That's supposed to equal the energy eigenvalue that we're also solving for. And what we did, we defined the energy eigenvalue to be h bar omega times a dimensionless quantity. So the h bar omega defines the energy scale of the problem. And then we defined the position to be in length scale times y. So this is a length scale, which we called b. And then the solutions that we found after doing a long argument about things being properly normalized, in other words, not blowing up at infinity, we found the allowed energy eigenvalues are h bar omega, the energy scale, times n plus 1/2, where n is a non-negative integer. Okay, and the n plus 1/2 is nothing other than the curly e sub n. Okay, and some comments about these. In this problem, and this is by no means a general feature, but in this problem of the harmonic oscillator, the energies turn out to be equally spaced. They're non-degenerate. That is a general feature. We proved that in one-dimensional quantum mechanics for bound states. So this is general for 1D bound states. Okay, this equally spaced feature is not general. Okay, and the difference in energies, delta E, is h bar omega. Here the delta is not to be confused with uncertainty. It's just the spacing. So this is the quantum of energy in this problem. And then the corresponding eigenvectors. So these were the eigenvalues. The eigenvectors we could call psi with a label n to tell us which integer we're talking about, or we should just use the common notation from now on, where we just label the kets by n. So those are the kets. The wave functions are defined then to look like this. So we can either call them psi n of x or x inner product n, and that's equal to, we found, m omega over pi h bar to the 1/4, square root of 1 over 2 to the n factorial. This is all to make it normalize to 1. And then the nth Hermite polynomial, and then a factor that makes the wave functions go to 0 at infinity instead of blowing up at infinity. So these were the Hermite polynomials, which you can look up in tables up to, or on computer up to very high n. And I want to emphasize that we made a choice here. We chose the complex phase of these things to equal 1. In other words, we chose them to be real. And that's going to be important that we recognize that this is a choice in a little bit when we do the momentum representation of the same kets. So in general, for a complete set of states, we should check orthonormality, which in this case looks like the following. We do an integral over all x, psi n of x star, psi m of x. That's delta nm. That's the orthonormality condition. Okay, and that's what all these factors again are for, to make that true. And here, the star actually doesn't do anything, but we keep it there for good form anyway. It does nothing because we happen to choose our wave functions to all be real. So by the way, choosing the wave function to be real is not the same thing as choosing the ket to be real. In fact, choosing the ket to be real is something that doesn't really make much sense. And again, we'll talk about that in a little bit when we talk about the momentum representation of the same kets. Okay, so we have an orthonormality condition. And another thing we can write down that's kind of interesting is recall that in the position representation, if I take the inner product of two position eigenstates, that's the Dirac delta function. Okay, that doesn't matter what problem you're talking about, whether it's harmonic oscillator or any other problem. It's just always a mathematical fact. But so now we can see what this implies for harmonic oscillator wave functions by taking a sum n equals 0 to infinity of xn and x prime. So I've just put in 1 as a complete set of states. So that's still delta x minus x prime. And now I can just rewrite this in terms of the wave function. So in terms of Hermite polynomials, this is sum n equals 0 to infinity, psi n of x, psi n of x prime star. Again, I'm just putting the star there for good form. It doesn't actually do anything. And so again, that's delta x minus x prime. Okay, so now what you could do is you could take a computer and you could try evaluating the sum, teach your computer what Hermite polynomials are and how to evaluate them, and do a sum. Of course, on a computer, you can't really sum to n equals infinity. So what you would really do is sum up to some very large n where you think that's good enough. So what happens if you truncate this at some large n? So I'll call it m max, n max. Okay, then you could graph the left-hand side and see how it approaches the delta function. And if you do that, you get something like the following. So let me make a graph with the vertical axis is the left-hand side of that previous equation. And the horizontal axis is just x. And somewhere along the horizontal axis is the point x prime. Right? And then I could say, what does the left-hand side look like? And the answer is it has the following shape. So it looks like one of the forms of the delta function that we had, where the height of this is increasing as n max is increasing. In other words, as we put in more and more terms, we get a higher and higher peaked function. So that's the sense in which it's approaching the delta function. Whereas the width of this thing, the width of the main peak, as opposed to all the wiggles off to the side, that's decreasing for larger n max in such a way that the area under the curve, the integral of it, is approaching 1, which is what you expect for the delta function. Okay, so what we've done is by studying a particular problem, we have found a way of approximating the delta function in terms of the eigenstates of our problem by using completeness. Okay, some other facts about the Hermite polynomials. I'll just list them here. If this was a class on mathematical physics, we might take the time to prove all these facts. But I'll just list them. They're actually not too hard to prove. So facts about Hermite polynomials. Okay, so one of them, each one of these mathematical facts you can sort of translate into physics language as to what it means. One is if I take the nth Hermite polynomial as a function of minus y, that's minus 1 to the n power times the nth Hermite polynomial of just y itself. So that's telling you that these things are parity eigenstates. And in fact, the parity eigenvalue for the state labeled by n is, it's always 1 or minus 1, and here it's going to be minus 1 to the nth power. And so that you just read off what happens when you flip x to minus x. That's the same thing as flipping y to minus y. And so that's where this factor comes from. Okay, another fact is what happens if you take a derivative of a Hermite polynomial with respect to its argument. And the answer is you get back 2n times the next lower Hermite polynomial. So as a sanity check, the Hermite polynomial h sub n has degree n, that's the largest power of y. And so if I take a derivative with respect to y, I'm going to knock it down by the degree down by 1. So that makes sense. If you just plug the Hermite polynomials into the Schrodinger equation and then use this previous equation, you get another fact, which looks like this. Hn plus 1 of y is equal to 2y Hn of y minus 2n Hn minus 1 of y. So this is known as a recurrence relation. And so what it means is, let's say you know all the Hermite polynomials up to some n, then you know this and you know that. And so then you can plug in and find the next Hermite polynomial. So once you've got 0 and 1 for the Hermite polynomials, you can get any Hermite polynomial you want pretty easily just from this equation. Another way of doing it, if you don't want to do it by recurrence, is there's a way of just writing what the nth Hermite polynomial is in closed form, which sort of ironically is not the form of a polynomial, although it does result in a polynomial. And that looks like this. You take e to the y squared over 2, and then you act n times with this combination, y minus the derivative with respect to y. So when I write that to the nth power, I'm saying, take this differential operator, act n times, and you're acting on e to the minus y squared over 2. Okay, so that's a neat way of just, you can just compute any Hermite polynomial. Again, we could prove this, but actually there's a much easier way to prove it that we'll prove later. It turns out it's much easier to prove in the energy representation rather than the position representation that we're using right now. Okay, and then here's another one. If you take the sum from n equals 0 to infinity, so we're summing over all the Hermite polynomials. But now I'm going to put in a factor of t to the n over n factorial. Here, t is not time, it's just some parameter, some quantity. So if you do that sum, you get, it turns out, a neat expression. You just get the exponential of 2yt minus t squared. So that right-hand side is what's called a generating function. It's just a simple function which, when you expand it out into powers of t here, the coefficients up to this normalization of n factorial, the coefficients are Hermite polynomials. So it's a common thing that when you have special functions that are solutions to differential equations, you can write them, you can write relations of them involving a generating function of this type. Okay, so with all those things, you can now construct any Hermite polynomial you want. And so just as some examples, we can look at, for example, what's the ground state? Ground state means lowest energy, which in this case is going to be n equals 0. And so I'm going to graph this as a function of x. And what I'm graphing is the wave function. Psi 0 of x is m omega over pi h bar to the 1/4 times the exponential. I'm going to go ahead and plug in what y is. So this is minus m omega x squared over 2h bar. Okay, and the shape that it has, because the lowest Hermite polynomial is just 1, the shape that it has is just a Gaussian. There's no wiggles in it, just has this shape like that, where the points at full width have maximum. Here are square root of h bar over m omega and minus square root of h bar over m omega. Because that's the length scale in the problem, it's sort of, basically it has to have that shape. Okay, then we can do the same thing for psi 1. Psi 1 does have a wiggle in it. So I'm going to make sure I draw my axis so that it can go negative. This is just a graph of psi 1 of x versus x. And the shape is, it goes through 0 because it's parity odd. And it does something like that. Okay, and similarly, we can do psi 2 of x. So here's as a function of x, psi 2 of x. Okay, and given our phase conventions, it's actually negative down here. Oops. My pencil is trying to make me draw a straight line, even though I don't want to. It looks something like, it goes negative, positive, like so. Okay, and then let's just draw psi 3 of x, just to have some examples. So psi 3 of x, the 3 is an odd number. So that's telling us that it's going to be odd parity. And so it's going to go through 0 here, and it goes through 0 kind of like that. Oops. Again, my pencil thinks it knows when I want to draw a straight line, and it's not correct. I don't want to draw a straight line, pencil. So it does something like that. This is psi 3 of x. Okay, and then finally, let's draw something for a nice large value of n. So this is psi, let's do psi 10 of x just to choose something. And actually what I think I'll do is I'll draw the square of it so I don't have to worry about it going negative. Okay, so what does the shape of this thing look like? It's approximately the following. So it has a shape like that here, and then it's got a bunch of wiggles. And the wiggles start getting larger as I get farther away. I don't know if this is actually side of the 10 or not, but it's 1, 2, 3, 4, 5. I think I did side 12 by accident. Okay, but the wiggles get bigger until they finally get to the last wiggle. This one maybe, oops, it took out the whole thing. Okay. I'm trying to draw these to illustrate that they get larger and then they die off exponentially. This is as a function of x. Oops. Okay, and then right at the edge of the last wiggle is what's called the classical turning point. Okay, and the classical turning point is beyond that, the classical particle is forbidden, but the quantum particle has some small probability of being there because the wave function squared is not quite 0. It's just going down exponentially. Okay, but it's forbidden there, and it's allowed inside where all the wiggles are. And the fact that the wiggles are getting larger towards the edge is telling you the classical particle is more likely to be found at large x. If you measure its position. So I should have said quantum, that the classical version of the same statement is that when you're near the turning point, the particle is moving very slowly. And so the classical particle is also more likely to be found near its turning point because it's just going very slow at that position. To be found at large x. I should say when n is large. And the larger n is, the more likely it is to be found, the particle is to be found near its turning point. Okay. Any questions on that so far? All right, so everything we've done now is in the position representation, and I said we were going to do this 3 ways. We've done the position. The next thing to do is the momentum representation of the harmonic oscillator. And here we can reduce our labor considerably by noticing that we've already done pretty much all the hard work. So what are we after? We're after the momentum space wave function of the ket n. Like so. And the Hamiltonian is, of course, the same thing it was. And we notice that we can almost take p and replace it by x. It's just that in the Hamiltonian, they have different coefficients in front of them. The other thing that's important is the commutation relations, where x commutator with p is I h bar. And so that would be the same if we replaced x with p, but then there would be a minus sign, so we have to replace I with minus sign, with minus I. Okay, so the whole problem is unchanged if we make the following replacements. Okay, first of all, we're going to take x and interchange it with p. And then because of this commutator, we're going to take I h bar and replace it by minus I h bar. So I here gets replaced by minus I. And then we have to take the coefficients here in the Hamiltonian. And so 1 over m is going to be replaced by m omega squared. Okay, so we can write that as 1 over m gets replaced by m omega squared. And so if we make all of those simultaneous changes, then everything in the problem is just what it was before. And so we don't have to redo all the work of writing down possible solutions to the differential equation and plugging them in and solving the recurrence relation and figuring out what integers are allowed. We can just write down the answer. And in preparation for doing that, note or recall that psi n of x, the way we wrote it, depends on a length scale. Oops, there's no 2 there. Square root of h bar over m omega is a length. Okay, and so when we write down the correspondence between position wave functions and momentum wave functions for the same ket, what are we going to do? We're going to use our rules here, especially that one, and we're going to say, okay, we should take square root of h bar over m omega and replace it by square root of h bar m omega, okay, which is a momentum scale instead of a length scale. Okay, and this wave function is xn, and this momentum wave function is Pn. Okay, so now what we've learned here is that in order to write the momentum wave function, we should use this momentum scale. And so we'll just make a definition out of that. We will define a dimensionless variable v, which is going to be p over square root of h bar m omega. Okay, and then we can immediately write down what the psi tilde n's of p are. The momentum space wave function is equal to, I'm going to write a denominator here with a mysterious space above it. Okay, but I've just basically replaced square root of h bar m omega by square root of h bar m omega. I've got my factor of 1 over 2 to the n factorial square root. I've got a Hermite polynomial, but instead of a Hermite polynomial of y, it's going to be a Hermite polynomial of v. And instead of e to the minus y squared over 2, it's going to be e to the minus v squared over 2. Okay, so all these steps just deriving this are going to be exactly the same. We could go through them all again, but it's literally the same thing. The only change is that, remember, we made a phase convention choice for our kets in order to make the position space wave function real. And once we've made that choice, we can't make it again for the position space wave function. So it turns out that we need a phase here, and that phase turns out to be minus I to the nth power. It's just a constant phase there. But the reason it has to be there, this phase convention, it's there to ensure that we're being consistent in the following sense. This thing we've just written down, Pn, should be, by completeness, integral from minus infinity to infinity dx of Px xn. And this thing we already chose the phase for. So we don't get to choose it again. And once we choose that phase choice for the position space wave function, that determines what the phase is for the momentum space wave function. And it turns out it can't be just real. Well, it can be for n equals, I guess a multiple integer multiple of 4. But for everything else, that it actually gets a phase factor. So for example, a nice example is the ground state. because for the ground state, n equals 0, so we don't have to worry about that phase. And then psi tilde 0 of p is equal to 1 over pi h bar omega m to the 1/4. This square root factor doesn't do anything for n equals 0. The Hermite polynomial is just 1. And so now we can just plug in for this exponential. And so we get here is, what we get here is e to the minus p squared over 2m h bar omega. Okay, so that's also a Gaussian. It's true for the harmonic oscillator that the ground state only happens to be a Gaussian. And once it's a Gaussian in position, we proved earlier that Gaussians are Gaussians regardless of whether you're at positional momentum. And so, sorry, is somebody asking a question?
Yes, I have a quick question. In the psi squiggle p up there where you include the entire equation, in the denominator, should that be pi h bar omega m for mass?
M for mass is correct. Very good.
Okay, thanks.
Okay. Other questions? No? Okay. All right. Let's see, where were we? So the ground state is a Gaussian, and then you can work out, because we know all the Hermite polynomials in principle, one could go ahead and choose what they are. But so again, once you've chosen the phases for the position wave function, which history tells us we should choose them to be real because that's what everybody else does. But then you have to be careful that the momentum space wave function have a different phase. There's just no way around that. Okay, so we're actually done with the momentum representation. That took almost no extra work, as promised. And so now we're going to go to the third and the easiest way to solve this problem. And that's the energy representation, which is actually a method given first by Dirac. And so the advantages of this is, it turns out any calculation you want to do is probably easier in the Dirac or energy representation. The disadvantage is it's a little bit mysterious how you would guess this starting from nothing. And the other thing is it doesn't apply to many other similar problems that aren't the harmonic oscillator. So the idea here is we're just going to define raising or creation operators. Okay, and that's defined as a dagger, which is square root of m omega over 2 h bar times the position operator minus I times square root of 1 over 2 h bar m omega times the momentum operator. And then if you take the Hermitian conjugate of that, you get the lowering or annihilation operator or destruction operator is just the Hermitian conjugate. So everything in the square root here is just real numbers, so nothing happens to that. X is a Hermitian operator, so nothing happens to that. Minus I becomes plus I, because we know we take the complex conjugate. And again, P is a Hermitian operator, so nothing happens to that when we take the Hermitian conjugate. So we're defined, this is just a definition. It's going to turn out to be useful. And again, one could have perhaps guessed these definitions just by the fact that what we've put in here is something with units of 1 over length. And what we've put in here has something with units of 1 over momentum. And so what we're ending up with is dimensionless operators, A and A dagger. Okay, so these are dimensionless. So that's maybe the one clue that this is a good thing to do. The factors of square root of 2 are maybe less obvious, and they're there sort of for future convenience. So if you've made those definitions, then you can express X like this, A plus A dagger. And momentum is I times square root h bar omega m over 2 a dagger minus a. Okay, so those are equivalent definitions. And now if you want, you can take the a dagger and a expressions, and a thing you often want to do with operators is figure out their commutation relations. And if you do that, you get a commutator with a dagger is equal to 1. This is a very important equation. And this comes from the fact that the commutator of x with p is I h bar. So notice one thing that happened is the h bars appearing everywhere in these expressions sort of miraculously got out of the way. So did the m's and the omegas. And so everything is designed in order to just give a nice dimensionless number of 1 for the commutator here. So now that we know the commutator, we can go ahead and, for example, figure out what the operator a dagger a is. Turns out that's a useful combination. And so you just plug in the definitions and multiply through all the operators, and you get the following. M omega over 2h bar x squared plus 1 over 2h bar m omega times p squared. And then there's the cross terms, which arrange themselves into I over 2h bar commutator x with p. But that we know is I h bar. And so this whole thing, this last term, just comes out to be minus 1/2, which is kind of neat because it had x and p in it both, but then the way these functions are defined is a conspiracy to make this thing be not an operator, but a number, or really just a number times the identity operator. Okay, so that's one conspiracy. And the other conspiracy is that this stuff is almost the Hamiltonian. In fact, it's the Hamiltonian divided by the energy scale to make it dimensionless. So it's capital H over h bar omega. And so rearranging that, what we found is that the Hamiltonian is equal to the energy scale, h bar omega, times a dagger a plus 1/2. So that's good. It means we've written the Hamiltonian in terms of our raising and lowering operators. And so now, again, a good thing to do is to know everything that you can about commutation relations of all your operators in your example. So we can compute things like commutator of h with a, which is h bar omega commutator a dagger a with a. We can forget about the 1/2 because it's just a multiple of the identity. It commutes with everything. Okay, and so we can write this as h bar omega a dagger a minus a dagger a, which arranges as the commutator a dagger a, which we know, times a. And so that works out to minus h bar omega times a. Okay, it would be also, it's also useful to know the commutator of h with a dagger. Okay, and that you can do the same way, or you can actually take the Hermitian conjugate of the previous equation, and that works out to h bar omega without a minus sign times a dagger. Okay, so here's why this is useful. Oh, and by the way, we're going back to the beginning. We're not pretending, we are pretending that we don't know what the energy eigenstates are, because we're just going to work them out as if we were starting from scratch. So I'm not going to assume the energy eigenstates are labeled by integers n yet. We're going to prove it. Okay, so suppose we have an energy eigenstate. I'm not going to label it by n. Instead, I'll just label it by E, and we'll figure out what E is later. hopefully with the same answer. So I'm now calling it E. Before I called it psi, just for variety. And now suppose I act with the Hamiltonian on the state A dagger E. So I can write that as the following. I can write it as the commutator of H with A dagger plus A dagger H acting on E. And the nice thing about writing it that way is I know what H is acting on E. It's the eigenvalue, E. And I also know what the commutator of H with A dagger is because we just worked that out. That's H bar omega A dagger. And so this is equal to energy eigenvalue plus H bar omega times E again. Okay, now if I take E and I act with A dagger a bunch of times, what this shows is every time I act with it, I'm just going to be adding H bar omega to this expression. And so what do we learn from this more generally? What we've learned is that if I take A dagger, act with it n times on an energy eigenstate, then I get back an eigenstate of H with energy. That's the original E plus n times H bar omega. Okay, and so we've constructed a new energy eigenstate out of an old one. And similarly, I can do the same exact exercise, but instead of with A dagger, with A. So if I act with H, acting on A times E, that's E minus H bar omega times E. Okay, basically the only thing that changed here is that instead of using this with an H bar omega, now I'm using this with a minus H bar omega from the commutator of H with A. Okay, and so what we learned from that is that if I act n times with the lowering operator on an energy eigenstate, I get an eigenstate of H with energy E minus n H bar omega. And so if we contemplate that, if we start with any state that we think is an energy eigenvalue or energy eigenstate, we can construct an infinite chain of other states that are also energy eigenvalues. And they all differ by integer multiples of H bar omega. So the chain of states looks like this. I should say stationary states. Okay, it's E minus 2 H bar omega. That's the name of the state. E minus H bar omega. E plus H bar omega. E plus 2 H bar omega, etc. Going off in both directions. Okay, so energy is going to the right here. So the problem is that we proved that this cannot happen because the first thing we did when we were considering the harmonic oscillator Hamiltonian is we proved that all the energy eigenstates had to be positive, and yet these ones seem to be going off to negative infinity. Okay, so, but we proved that the energy eigenvalue for a harmonic oscillator state is always greater than 0. We also proved that in the position representation, but we're even ignoring that. We just proved it on general grounds. So what does that mean? It means that some of these states in this infinite chain that we constructed have to be not there. They have to be fake or null kets. So that means one of these at some lower value of E has to be the null ket. And then when we go to the left, we're just acting on the null ket over and over again. And so we get more and more null kets, which aren't physical states. In other words, one of the states in the chain has to be the lowest thing you can get that's not a null ket. Okay, so that means one of states in chain, not necessarily the one we started with, labeled E. So let's call it 0, must have A acting on it be the null ket. And by the way, the 0 here does not mean it's the null ket. It's the label for the thing that we act on to get the null ket. Okay, and then if we do that, then all kets that we thought we constructed with lower energy are actually not there. They are of the form lowering operator to some power acting on the state 0, don't exist as physical states, they're null. Okay, and so in particular, that means if I take a dagger and act on the state A0, which we now know is the null ket by definition, anything acting on the null ket is 0. So we know that's true. And that means if we take Hamiltonian over h bar omega, subtract off the 1/2, that makes it A dagger A. And we act on 0, we get 0, which is telling us that H acting on the state 0 is h bar omega over 2 acting on 0. And so what we've proved is that the lowest energy eigenstate has energy h bar over omega over 2. Okay, and that is agreeing with what we found in the position representation. So that's good. Now, one loose end is you could ask, well, could there be more than one such state 0? And the answer is no. So could there be more than one state of this type? Which if they do exist, we prove they all have the same energy, h bar omega over 2. And the reason it can't happen is we proved a general theorem that energy eigenstates are not degenerate for bound states in one dimension. We proved that in a previous lecture. So bound states in 1D have non-degenerate energies. Okay, so that means that our set of states is just labeled by, so the energy eigenstates are 0 and 1 and 2, just like we found already in the position representation. They go up to infinitely large energy in the positive direction, but not in the negative direction. Okay, so we're out of time for today, but next time what we'll do is we'll figure out how to construct these states from the creation operator and get their normalization correct. So construct and normalize these states using a dagger. And then we'll do a couple of examples showing how much easier it is to use this rather than the position representation. Okay, so that's it for today. Are there any questions?
I had a question about the homework, but if someone else has a question about the lecture, they should go first.
Apparently not, so you can go ahead on the homework.
All right, so I had a question about number 4A on the homework, because it says write expressions for X and P in terms of A and A dagger. Do you want us to derive that or just write it because you list it in, you wrote it in the notes today and in the textbook?
Yeah, so really that's a freebie. You're supposed to derive it, but I've already given you the answer. So it should be sort of a 2-line derivation, basically.
Okay, thanks.
Yeah, but problem 4A is supposed to be free.
Okay.
There's nothing tricky about it. Okay, other questions?
Professor, I have a question.
Okay.
Hello, Professor. I'm sorry, I have a question from last time. I'm sorry, I was having some internet connection problems. So I watched the video, and there's 2 parts I had a question on. One is, it's a little bit minor. I didn't understand why you had changed from M to J in that first one. When you were, I think you were trying to figure out
Okay, let me
the, you can pull up your notes, I'll show you where it
was. It's probably just
right.
Go ahead.
I think it was I think it was either after this, if you scroll down a little bit. No, it was before this. I'm sorry, before this.
Okay.
Please scroll up.
Oh, is it perhaps here?
Yeah. You renamed M to J. Why was that?
Okay, so in our recurrence relation, we had 2 terms. There was this term, which we were sort of working on here. We were trying to put this in a nicer form. And then we had the other term, and both of them were sums over J. So the idea was, what we wanted to do was we wanted to make this into a nicer form. To do that, we had this change of variables that we're summing over, namely J to M. But then in the end, we want to combine it with this term again. And so that's the only reason. We wanted to rename it so that they're both sums over J. And so when we rewrite it, we can combine them into a single sum over J here. That's the reason for renaming M to J. So it's kind of a sneaky trick. It's just we wanted to rewrite this. So really the strategy was, we're having sums over J, but one of them had y to the J, and one of them had y to the J minus 2. And what we wanted was for both of them to have y to the J. So we did this sort of 3-step relabeling process to turn the y to the J minus 2 into a y to the J. And then we can combine them with a single coefficient.
Okay. So we can do that basically, correct?
Yeah, so as long as you're summing over some integer, it doesn't matter what you call it. I could have called it Q or Z or anything else, as long as I'm summing and as long as I keep track of what the limits of the sum are. That's the other tricky thing you have to make sure of, but that's what we did there.
And the other question I had was further down. You mentioned that U was not an infinite series, but a polynomial. what was
That's right.
meant by that?
That's because it terminates.
Oh, so then it becomes from an infinite series to a finite polynomial, correct?
That's correct. Yeah.
Okay. Thank you. That's it for now. You'll post this one as well, correct? Because I joined a bit late.
Oh yeah, of course. I always post them.
Okay, thank you so much.
Sure. Let me stop the recording here.